So we're going to be talking about position versus time and velocity versus time graphs today. We're going to look at them from a couple of different perspectives. We're going to look at them from the perspective of what can I interpret from this graph and what can I calculate from this graph. Both of those skills are really important. Okay? What I want to stress to you is this. I'm going to go over this and I'm going to talk about a line of thinking. Here's how I want you to approach a graph. Here's how I want you to think about a graph. Rather than memorize what this is. Memorize what I can get from this graph. I don't want you to do that. Okay? Memorization in physics is the last nail in your physics coffin. There's too much to memorize. Okay? Your epitaph will read, I tried to memorize everything in physics. You can't. Okay? There's too much. In fact, even in biology, which people think is all about memorization, even though that's wrong, okay? It's not about memorization. You can't memorize everything. You need to be able to approach everything from a perspective of, okay, what is this trying to show me? And now, what does that mean I can get? Okay, that's how we want to approach, especially graphs. What is this graph showing me? And what can I get from it as a result of what it's showing me? Okay, not a, okay, on position time graphs, this represents this, this represents this. Because if you try to do that, you get through Science 10 that way. Maybe even through Physics 20, where we only have about, a dozen different graphs. When you get to Physics 30, you're looking at 30 plus different types of graphs that you could get on a diploma exam. Okay? It's not that you'd get all 30, but you'd have to know and memorize what you can get from 30 different graphs. And that would mean memorizing probably between 3 and 6 different things for each of those 30 graphs. You're just not going to be able to do it. Okay? So, approach each graph from the perspective of what's here, what does that mean I can get? Alright, so we need to understand what information can be read just by looking at a kinematics graph. What can I read off of this graph? What is it showing me? What's happening? Okay? Understand how graphs and equations from kinematics show the same information in different ways. Okay? Just yesterday I showed you how, or sorry, not yesterday, but on Friday, I showed you how the slope of the line on the position time graph represented velocity because it was really like just using v equals over t. Okay, I'll go over that again today, but okay, that's what we're talking about there. Okay, and learn that kinematics equations are derived from graphs. Okay. So position versus time graphs are what we're going to start with. So these are both position versus time graphs. Now, on this position time graph here on the left, okay, what is my initial position? 20 meters. Okay, at time 0, the position of the object is 20 meters. Okay, it doesn't give a direction there, so we would have to just say like 20 meters forward or positive 20. Okay. What is the object doing in the first second? Nothing. Okay. How do we know that? Right, because at time 1 second, the object is still at a position of 20 meters. So it hasn't moved. Okay. So anytime we see a horizontal line on any kind of graph, it means that nothing is changing, at least on the y-axis. Nothing is changing. There's something changing on the x-axis. Yeah, time continued to move forward. For 1 second, the object sat there, okay, and did nothing. Now, what is the object doing between 1 second and 3 seconds? It's moving at a constant speed or at a constant velocity in a forward or positive direction. Okay, now, how do I know that that line is showing me something moving at a constant velocity? Right, each second that line goes up by the same amount. Okay, and again, that's something that's true for any graph. In this case, it happens to mean the object traveling at a constant speed. But if this was a graph of mass over time, then it would say the object was gaining mass at a constant rate, whatever time interval. Okay? A diagonal line means that there is a linear or constant rate of change over time or whatever's on the x-axis. Okay? So it's not a matter of having to memorize. It's just a matter of looking at the graph and saying, okay, position is changing. It's going up by the same amount over time. Okay, well, I just interpreted that a constant change in position over time means traveling at a constant, well, or velocity in this case, yeah. Okay, everybody all right with that? It's not something I have to memorize. It's something I can interpret off of the graph. Okay, what is the object doing between 3 and 4.5 seconds? Nothing, yeah. Its position doesn't change for a second and a half. Right? What's it doing between 4.5 and 6 seconds? It's moving backwards at a constant velocity. Again, it's a line, right? It's not a curve, it's a line. What's the overall displacement of this object? 0. How do we know that? Right. Its initial position and its final position are the same. Okay, so that means it went forward, but then it came backward, and it ended up where it started, so its total displacement is 0. How far did it go? Okay, well, let's look at how we figured that out. I see a few people have kind of figured it out, but let's see how we figured that out. Okay, how far did it go between 0 and 1 second? Nowhere. Didn't go anywhere. Stationary. Okay? Its initial position was 20, its final position was 20 at the end of 1 second. Okay. At time 1 second, its position is 20 meters, but at time 3 seconds, its position is 60 meters. How far did it go? 40 meters. Okay. How far did it go here? 0. How far did it go here? Another 40, right? It went from 60 back to 20. Now, because I said how far, it doesn't matter that that 40 is backwards. It would be negative if I was doing this from a vector perspective, which is why our displacement would be 0. Okay, went another 40 meters here. So its total distance traveled is 80 meters. Okay. Everybody okay with that? What's the average speed? Nope, not 20. What's my total distance? Remember, average speed is total distance over total time, right? So 80 divided by, okay, so what, 1.26? So 1.6. How about I just use my calculator to stop being lazy? I was thinking 60. I went 80 over 60. That's what I was thinking about. Yeah, 1 point. Okay, so we're looking at 80 over 6 is 13.3 meters per second. There's my average speed. All right? Did I have to memorize anything there, or did I just figure it out? I just figured it out. I remember that B equals D over T. This graph is showing me D and T. I can get what I need from there to do a calculation. Okay. All right, so those are the kinds of things you might encounter on, let's say, a quiz, like on Thursday. Now, this graph on the right looks different. There are no jagged lines. There's one curve. Okay, so the curve tells me that position is still changing, but it's not changing in a uniform fashion or in a constant fashion. Okay, it's changing exponentially, really. Okay, but its rate of change is not constant anymore. Okay, so in the first second, the object only goes that far. Right? But in the second second, it goes that far. And in the third second, it goes even further, and then even further still, and even further still. You can see that, right, the distance between these lines keeps getting wider. Okay? The only way to go further in the same time interval is to go faster. Just to show, okay? Showing an accelerating object. Again, that's not something you need to memorize. Okay? You don't have to memorize that a curve on a position time graph means the object's accelerating. You can see that. Okay? You can read and interpret that. That's going to be something you're going to be asked to do. Okay? It's very easy to make a multiple choice question that just has a graph on it that says, according to this graph, what does the object do? A, traveling at a constant speed in the forward direction. B, traveling at a constant speed in the backward direction. C, accelerating forwards. D, accelerating backwards. Okay? You follow me there? Right. Now, this acceleration is a positive acceleration because the object's going faster and forwards. Okay? If the graph looked like this, that acceleration is, yeah, it's negative. Okay? Because the object's slowing down. Okay? Still in a positive, it's still moving in a positive direction, but it's accelerating backwards. Yeah, I'm seeing some of those looks like, wait, no, you can't go forward and accelerate backwards. Yeah, you can. That's how you slow down. Okay? You can totally accelerate in an opposite direction to what you're moving. Watch, I'll show you. While the marker is moving up in the air, it's accelerating downwards. That's gravity, by the way. Okay? When I throw this thing up in the air, as soon as it leaves my hand, it's already starting to what? Slow down. What's causing it to slow down? Which way is gravity pulling? Down. It's accelerating downwards. That's why it slows down. That's why I can't throw something into orbit. Okay? If gravity didn't make this thing accelerate downwards, I could throw it and it would travel into orbit. That'd be bad because the same logic would apply to jumping. Okay? So gravity can make this thing accelerate. So while this thing is traveling upwards, it's accelerating downwards. And eventually it stops. And then starts to both accelerate downwards and move downwards. Okay? The whole time it's in the air, it's accelerating downwards. It doesn't necessarily have to move in the same direction it accelerates. Eventually it will. Okay? That's how acceleration works. Unless we're talking about your brakes. Okay, yeah, because your brakes rely on a force that can't propel something, okay, they can't actually make you go backwards. They can make you accelerate backwards, but they can't propel you backwards. And that's usually where people have that block, that mental block. Like, well, when I slam on the brakes pedal, I don't go backwards. Yeah, good thing. Okay, that's why we have brakes. Otherwise, the only way to stop would be to jam your car in reverse, and that would mean you would eventually go. Well, probably not. Eventually go backwards. Okay. The same thing would be true if I put a bungee cord across the front of the room, okay, and I just run into the bungee cord, okay, which is funny because I end up on my butt, okay. But okay, if I run into that bungee cord, as soon as I hit the bungee cord, what's happening to me? I'm accelerating backwards. Yeah, that's why I slow down. Okay, I keep moving forwards for a little while, okay, but eventually I get thrown back. Okay, that's how bungee jumping works. It works. Okay. You jump off a bridge with the bungee cord, okay, you're accelerating downwards. Once the bungee cord starts to pull, you're accelerating upwards. Hopefully the person did the calculations right. Okay? And it pulls upwards enough that you don't hit the bottom. Okay. Yes, that's exactly what we do. You don't want that. Okay, so is that making sense so far? So, things we can read off of a position versus time graph. Okay? If I look at this graph here on the left, can I tell where the object is at all times? Yes. So one of the things I can read off a position time graph is position. And the other thing is time. That's true for all graphs. Okay? Whatever's on the graph is what you can read directly. Okay? I can calculate a few other things from this graph. I can calculate the displacement. Because position is on here, and displacement is really just a change in position, I can calculate the displacement. Okay with that? Right? I can also calculate average velocity. Okay? Because I would be able to calculate the total displacement, and I would be able to read the total time. So I can make that calculation as well. I could also get the average velocity if this graph had just one single line by using the slope. Okay, so let's have a look at that again. It seems like we forgot about that. All right, yesterday you built graphs that looked like this. They were of an object traveling at a fairly constant velocity. Okay? And then Google Sheets spit this out for you, except they don't put the Y there anymore. They used to. Okay? And it would say something like 0.652x plus 0.28, or something like that. Okay? So they spit out the graphing equation. That's the equation for the line. Okay? Position is on this axis, and it's in meters. Time was on this axis, and it was in seconds. So if I use this equation to calculate a y value, I'm calculating the object's what? Position at whatever x is at whatever particular time. Okay? If I'm calculating an x value, then I'm calculating the time it takes to reach a certain position. Right. Slope tells me the relationship between my changing position and my change in time. And the relationship between change in position and change in time is velocity. Okay? So here's how this works. We calculate displacement by taking the final position and subtracting the initial position. And we divide that by time. Okay. If I set this up and I want to solve for the slope, remember that this is y equals m times x plus b. Okay, so if I want to solve for the slope, I'm solving for m. Okay, so to solve for m, I'm going to subtract b, so I'll have y minus b, and then I'm going to do what with x? Divide by x. Okay, does that formula look a lot like that? Because they're the same thing. Y values on this graph represent position. Okay? X values represent time. Okay? So when I take a y value, whatever it is, okay, that would be my final position. So let's say I'm using this spot right here. Okay? That would be my y value. And b is my initial position. It's the position at time 0. Okay, so this is really final position minus initial position divided by time. It really represents velocity. But it takes into account all of the points on your graph, which makes it more accurate than just doing this. Okay, taking that point and dividing by the total time only takes into account that point. Okay, and that's the mistake people make, because on our graph yesterday, our points probably went something like this. Right? They weren't all in a perfect line. Okay? But Google Sheets drew a line that went like this. Okay? If I just go v equals d over t and use this point, am I finding the slope of this line? No, I'm finding the slope of this line. Do they have the same slope? No. This line, the one that Google Sheets drew, is more accurate because it's an average of all of the points we took. If I just use v equals d over t, I'm only using the last point. I might as well have not measured any of the other ones. Okay, you guys follow the difference there? Okay, so if you're given the graphing equation, use the graphing equation to solve for things. If you're not, then you can use v equals d over t and use a single point. Okay? So basically, you would use the graphing equation if you had one line and the equation. You would use v equals d over t in a situation like this, because you don't have a single line here. Right, all right with that? All right. So is that relationship making sense there? Okay, you're going to find that this is true for basically all types of graphs. Okay, the equation will represent something to do with those two variables. Okay, when we get to velocity versus time graphs, we're going to find out what the change in velocity divided by time represents. Same idea. Okay. So with our slope calculations, okay, some of you may have learned to calculate slope by going rise over run. Okay, does that sound familiar? Okay, so when you do rise over run, basically what they tell you is go y2 minus y1 over x2 minus x1. Okay, and then you get your slope, and that's fine. The problem with rise over run is all it calculates is slope. Okay, y equals m times x plus b can help me calculate y values, x values that are not on the graph, beyond the graph, or on the graph. It can do both. Okay? It can calculate more than just slope. But where they get this rise over run value from is when they manipulate this equation for m. Okay? Because when that's manipulated for m, it's y minus b, which is y2 minus y1 over x. Well, remember that we don't put x2 minus x1 here because x1 is well, at b it's 0. So we don't bother putting that in there. Okay? It's the same equation. It's the exact same equation. But with y equals mx plus b, I can manipulate that to solve for other things. Okay? Rise over run, none. We typically don't use it as much, okay, in business. So you're right with that idea. Okay? The rest of that was just to show you that the slope equal b over t. All right, now, looking at this graph here. So this is a position versus time graph. Okay, so I'm going to treat this like I would treat an exam question or a quiz question. I'm going to ask you guys to calculate a few things from this graph. Okay, I want you to calculate the average velocity. Okay, should all be done. Why is it 0?
Displacement is 0.
Right, the displacement is 0. See, those are things you can recognize right away. Okay, what's my initial position? 0. What's my final position? 0. Okay, well then I can go with it. Okay, my average velocity is 0. Now I'm going to give you one that's going to require like a lot more time. What's the average speed? I'll give you a few minutes. That's going to take me a little while. Okay, I want you to calculate the average speed, assuming this thing goes all the way to 18 seconds. Okay, so there's basically like a little flat line here along the 0 that goes to 18 seconds. All right, give you a couple minutes to calculate the average speed. So what I have to remember here is, or first off, what I have to see on this graph is that I have an object that's doing a lot of different things. Okay, it's not just traveling at a constant speed, right? I'm going to calculate its average speed, but it's definitely not traveling at a constant speed. How do I know that? Yeah, the line is all over the place, right? I mean, there's times where it's going forwards, there's times where it's not moving, there's times where it's going backwards, okay? Not moving, going forwards, it's doing all kinds of different things, okay? So what I need to do then, if I want to calculate average speed, is I have to remember, how do I calculate average speed? Average speed is total distance over total time. Okay, so that means I got to calculate how far this thing goes in total. All right, well, I can eliminate part B and I can eliminate part D because in part B and D the object doesn't go anywhere. It's stationary because the position doesn't change. All right, in part A it goes from a position of 0 to a position of 6 meters. All right, that means it traveled 6 meters. Then during part C it goes from positive 6 meters to negative 10 meters. How far is that? 16 meters. Okay, and then between parts E and F, it gets back to the x-axis where y is 0, so it goes from negative 10 to 0, which is 10 meters. Okay, so that means that we go 32 meters. Okay. And that takes 18 seconds. Can I calculate my average speed? Yes. It's like, what, 1.8? All right, everybody okay with how that one worked? Okay, where is the object going the fastest? You know, nope. I think it's going fastest in E. E looks the steepest. Okay, so here's what I'm saying, guys. The steepest line on this graph is where the object's going the fastest. Okay, because during the steepest part, it covers the most distance in the shortest amount of time. Okay, again, that's not me memorizing that the steepness of the line equals speed. It's me just thinking logically. Okay, furthest distance, shortest space of time, that's fast because that's G equals D over T. Okay, so E looks the steepest. It looks a little bit steeper than C. It's definitely steeper than A. Definitely steeper than F. Okay. In what parts of the graph is the object moving forward? A, E, and F. Okay, now I see a few people looking at that going, that doesn't feel right. E and F are negative. Just because I'm behind where I started doesn't mean I can't be moving forward. Okay, like here, basically this is what's happening on this graph. Okay, if I start right here, right, I walk forward 6 meters, and then I walk backwards. I can't walk backwards 60 meters because I have to walk through the wall to do that. Okay, so I go back to here, and then in parts E and F, in part E I'm like, and then part F. Okay, I go a little bit slower. I feel just like my old high school physics teacher. That's exactly the kind of thing he would do. He would do all these like weird like motions with his body in front. Yeah. I just had this flashback to Mr. Hill, covered in chalk. We had chalkboards. Okay, doing one of those. Okay. He was honestly like the world's greatest physics teacher. He would start the day all clean, nice shirt, tie, and by the end of period 1, he was yellow, just covered in chalk. He would do this, and then he wouldn't get the eraser. And then he would sit there and look at it, and get chalk all over his face, all over his shirt, and by the end of the first period, he was yellow, just covered in chalk. Okay, but it was fun. Okay, so does that sort of make sense? Okay, so I've asked you to do a couple of things on this graph. I've asked you to do some calculations. And I've also asked you to interpret, just from looking at the graph, what's happening. Okay? Those are the kinds of skills you're going to be asked to demonstrate. Look at a graph, tell me what's happening. Look at a graph, calculate this. Those are the types of things. Okay, move on to the next slide. Okay, sometimes we're going to get a position versus time graph that's going to have curves on it. And we've already said that curves mean the change in position is no longer constant. So the object must be accelerated. All right. So in the first part of this graph, the object is accelerating forwards, and it's going faster. Okay? Now, when we get to about here, actually, about here, that changes. Now the object isn't accelerating forwards anymore. Now the object's accelerating. Okay, how do we know that?
It starts to slow down and eventually starts going backwards.
Okay, exactly. It's starting to slow down. How do I know it's slowing down? The curve goes right the other way. In other words, the line becomes less and less steep. Right? It gets flatter. Okay? Here the line gets steeper. In part A, the line is getting steeper, which means we're going faster. Okay, but in part B here, okay, we see the line flattening, and then we see the object, right, it's going backwards. It's actually accelerating in the same way all through this part. Okay? During this part of the graph, the object is actually accelerating in exactly the same way. But what does it do right at the top of B? It stops, and it turns around. Okay. All right, what's happening in C? It's accelerating, but it's accelerating to a stop. Okay, because what's happening to the line again? It's getting flatter. Okay, this is weird. That's what we have to be able to interpret. Okay. This part of the graph, the line's getting steeper and going upwards. So this is an acceleration in a forward direction. Okay? Here, this part here is an acceleration in a negative or backwards direction the entire time. What it's also showing is the object stopping its forward motion and beginning to move backwards. Okay? During this entire part here in part C, the object is always moving backwards, but it's accelerating forwards. That's why you slow down. If you're moving backwards, you slow down by accelerating forwards. Okay? And that's what this is showing. Okay? That's interpretation. That's looking at a graph and being able to come up with what's going on. Now, occasionally, we don't do this much anymore because it involves you actually drawing the graph and drawing on the graph. We don't really do that anymore. We let the computer do that for us. Okay? But occasionally, a question would give you a graph, and it would say, what is the instantaneous velocity at some point. Okay? So let's say that A is no longer representing this whole line. It's representing this point right here. Of course, you might say, what is the instantaneous velocity at point A? Now, we've only looked at how to calculate average velocity. That's total distance or total displacement over total time. Now it's saying, how fast is it going at that moment in time? How am I going to calculate that? Well, no, actually, I'm not going to use Pythagorean theorem. Okay? Here's what I have to understand. During that entire part of the graph, the velocity is doing what? It's changing. I'm supposed to calculate how fast it's going during a change in velocity at one instant in time. Okay? Now, what I have to remember is that because this is a position time graph, the slope of the line represents velocity. But the slope on a curve is always changing. So here's what I have to explain to you. This is the only thing that I understood in university calculus. The first day. After that, I understood nothing for the rest of the semester. I passed that class by memorizing the examples in the textbook, writing them down on the final exam, and getting part marks for method. That was smarter than more than half of the people in that class. That's how I passed. I didn't actually pass, but it was on the curve. You only have to be smarter than half the people to pass. Don't try that. I do not recommend that for success. I was desperate and it worked. Okay? It was totally a last resort. Okay. So here's what I learned first day of calculus. I actually had a really good prof. He was really interesting. I just didn't understand. He said, a curve is an infinitely large number of infinitely small straight lines. Okay? And that makes more sense to me now than it did then. Okay? Because now, most of the pictures and videos that we watch are digital. And your pictures and videos are made up of millions and millions of tiny pixels. Your computer can't draw a curve. It can only put squares together. Because that's how computers talk. They talk in zeros and ones, ons and offs, squares. Okay? So if we have a large number of squares that are incredibly small, we can't really see the little squares. It looks like curves. It looks smooth because our eyes can't resolve, okay, the size of those pixels. Okay? So what he was basically saying was, this curve is made up of a bunch of little square pixels, but they're so small you can't see them. As long as I can find the slope of the incredibly small straight line that exists right here, I can find the speed of the object at that point. Here's the problem. That line is really, really, really small. I can't really do a rise over run calculation on it because I don't get a y2 and a y1 and an x2 and an x1 because it's this freaking big. Okay? But I could draw a line that's parallel to it and make it longer. Agreed? What do you call a line that's parallel to a curve at one point? A tangent. So what you do is you cheat. And you draw a tangent that touches the curve. That was not very good. Okay? That touches a curve at one point, but doesn't cross it. Okay? And by doing that, you get a line you can calculate the slope of. Okay? And the slope represents the speed of the object. Okay? At that point, and anywhere else. In fact, if I was to do this up here at B, what would the slope of that line be? Okay. Rare is supposed to mean 0. Right? So, if we do that, my tangent is horizontal. Which means that at that point, the object is actually stopped. Velocity is 0. See how physics always works? It just always works. All right, we're going to talk more about position time graphs tomorrow, and as well as velocity versus time graphs tomorrow.